Hello everyone. I hope everybody's doing fine today. A lot going on out there. I kind of stir the beehive, and all the bees come out, and they start attacking me, like the bear who wants that honey, and no matter what. And I get a lot of that. Anyways, what have we been doing this week? We've been doing working a little bit on what is irrationality. And the context of that is mathematical physics. Is mathematical physics rational, objectively rational? And so we try to establish some criteria to see if we can qualify the theories, right? We're referring to the theories here, right? We're referring to, is mathematical physics rational? And mathematical physics has primarily two branches. One is quantum mechanics, the other one is general relativity. It's got a third branch which is not having too much success, and that's string theory. And the string theorists mathematically are trying to unite general relativity with quantum mechanics. And the issue there, the central point of string theory is gravity. Because right now there's no way of uniting gravity from quantum mechanics, the equation's always right, with general relativity. And general relativity is considered to be proved. It's already a fact. All the mathematicians voted for it, and so it's a fact now. But quantum, it's got to have that graviton, and it's not there. They can't find it. And I guess they never will. You can't explain gravity with gravitons, with discrete particles. And so this takes us down first to, what is irrational. And I've established some criteria. I think we need to define these words to use them in some way. Adrian was suggesting the other day, we don't have to use the word irrational because that's kind of offensive, or people have different ideas about what is rational, what is irrational, and so on. And so he says use the word the word dog, the word tree.
I wouldn't say it was offensive.
Well, it is to some degree.
But that's not what I was saying.
Okay, but it's offensive in this sense that if you label someone's theory as irrational, first he'll think it's just your opinion, and second he'll say, oh, so you're saying that I'm irrational. Well, no, you're not irrational unless you believe in it. But again, that's attacking the person. You're really attacking the theory. You're trying to put some criteria where you can objectively say that it's not rational. And by this I mean it's not a part of science. That's the main point. If in order for it to be within science, it's got to be rational. That's why the definition of science is rational explanation. So that's where the word rational fits in. And then the question is whether we have objective criteria for that or just opinions like, well, you put that criterion in there because it favors your theory and nothing else. It favors your position. And I don't think that's what we're doing here. I'm almost convinced, if you look at the criteria, here's a list of it. Converting a concept into a physical object, the first one. It sounds like, to me, that's straightforward. I don't think anybody can challenge that. If you use a concept and you start moving it around, you say love moves mountains, you got a problem. And then there are other criteria there using key undefined words with which you make your theory, the ones that make or break your theory, and you don't define them or you don't use them consistently. And the theory doesn't follow from the assumptions, and also when people claim to describe when they're actually explaining, and when people claim to explain when they actually describe. And I wrote an article about that this morning. So these are the criteria I'm offering for what is something that is rational. And,
Irrational.
In this case, irrational. Or, you could twist that around and say, unless, if you meet any of those conditions, you are irrational. And if you don't meet those conditions, then you have a rational theory. And obviously, you're welcome to add and subtract as long as you can justify the additions and subtractions. Why is quantum mechanics irrational? Why am I labeling it as irrational? Mathematical physics first, now the branches, quantum mechanics. Why is quantum mechanics irrational? Well, the bread and butter of quantum mechanics is the particle. You can't live without a particle in quantum mechanics because that's what quantum means. Quantum is a packet of energy, or supposedly, and that's what they call, a particle, whatever that means to you. Some people visualize it as some kind of little dot that's moving. Other people have other opinions about it or other notions of it, and they say, look, we're not referring to a corpuscle. What we're referring to is something totally different. And so that's when you start, and these are the mathematicians that take that position. You say, well, then what are you referring to if you're not to a corpuscle? And here is what a particle is. A particle is an excited state of a field. There you have it, folks. Particle is an excited state of a field. You have a field, and it's the excited state of that field, or a portion of it, that they call particle. They refer to that region, right, of the field as a particle. What this means in that particular system may be in a vacuum state, 0 particles, or in various excited states of the field, 1 or more particles. So you either have 0 particles or you have a vacuum state, and I don't know what they mean by that because they never acknowledge that there is a total vacuum. They never define what they mean by vacuum. They say space is made of particles, so I don't know what vacuum is made out of. They claim to bring virtual particles from the vacuum, so I don't understand what vacuum means in quantum. They have all these different definitions for vacuum. But let's go with a field. A field is a mathematical entity, whatever that is, that exists throughout space and time. In other words, a field of one particle extends all the way to infinity, to wherever the edges of space-time is. One particle. It sounds like they're describing the rope, being interconnecting all the atoms in the universe. That's what it sounds like. They're saying there's something called a field, and there's a potential at each point in space around a particle, and that potential extends to different degrees all the way to the edge of the universe. It's like, in fact, they give you an example there. They said the temperature in a room. In principle, you can define a function that gives the temperature at any point x in the room at any time t. Fields are defined similarly. In other words, you have temperature in the room, right? And you have the heater in the center of the room. Well, as you work your way outwards radially from the heater, it gets colder and colder and colder all the way to the walls at least, right? So what happens? You take a measurement with your thermometer, and as you get closer to the heater, the temperature, the thermometer reads higher readings. And as you get farther away, it gets lower readings. That's what they call a field. It's the environment around a central point. And you can choose what your central point is, or what the radius of that central point is. You can just arbitrarily say, well, I'm going to choose only 1 meter or 2 meters or 3 meters or whatever. And then it says that's the classical field, by the way. Now, a quantum field is what you get when you quantize a classical field. That means you turn a region, right? You cut a chunk of that classical field that extends all the way to the wall. You cut maybe a sphere somewhere in the center of the room, right? And that's a quantized field, and that's going to be the famous particle of quantum. In this process, the field becomes a function that gives an operator at each point in space-time instead of a numerical value. And you're saying, what are these guys talking about? And here I've illustrated the field for you. This is a field, according to quantum, okay? And what you have is it's a mathematical concept, not a physical object. That's what the particle is going to be. It's going to be a portion of that field. And a field is not very exciting unless something happens. And what it has to do, it's got to vibrate. And the only way it's going to vibrate is if you add energy. So you have energy on your right side there. My energy is green, maybe yours is yellow, I don't know. And you infuse energy into the field. It starts moving all those bed springs, and it starts vibrating. And that field, and again, this is just a two-dimensional field here. What we're talking about is something that extends throughout all of space, radially, fills space completely. And all this is vibrating out there. And that's what they call a field. And that's the quantum field. The quantum field is simply a portion of that, and that's what they'll call the quantum. So again, we're talking about concepts within concepts within concepts. That's all they're doing. These are mathematical concepts and nothing else. And here you have a definition of a field more clearly. A field is an imaginary concept. Or you could say a mathematical concept postulated because we have no better explanation. That's the answer that you get for the word field. In the old days, when something like magnetism had an effect that didn't involve matter touching something, but was able to affect matter over a limited range, it was called a field. In the 19th century, it was discovered that light or radio waves, were vibrations or excitations in the electromagnetic field. In the early 20th century, it was discovered that matter was really tiny bits of stuff held together by fields, mostly electromagnetic field, but within the nucleus two other kinds of fields. And then as quantum theory developed, in which particles did not have always particular locations or states, it was difficult to continue calling the little bits of stuff particles. So what happened? Finally, quantum field theory postulated that everything is a field. Great. There is an electron field. For example, a particular electron is a packet of vibrations in that field. So in physics today, a field is an imaginary space-filling idea that vibrates if you add energy to it. That's what these people have concluded after 2,000 years of brainstorming. What do you think of that? Sounds great?
Aren't they essentially looking at the invisible, right? They're looking at the unseen.
Yeah.
And they're just saying, okay, since we can't we can't see what it is, we can't empirically deduce what is here.
Yeah.
We're going to dispense with the empiricism on the shape level. We're not going to care what it looks like or what it is or what it does. We do care what it does. That's all we care about. We just care, but we don't care about what it looks like or what the unseen would look like if it were seen. They're just saying, okay, this magnet or this gravity, let's say this planet, all right? This planet is pulling on this moon with some unseen force that we'll never be able to see. So forget what it looks like. We're just going to look at its effects, and we're just going to keep it invisible. We're just going to say, okay, anything that's invisible, we're basically going to call a field. Anything that's invisible that acts upon other objects, we're going to call a field. I mean, for that matter, they might as well call gusts of air fields.
Yeah.
If someone blows on a pencil and moves it, they
First,
might
let
as
me
well
stop
say,
you. Do we have image?
Yeah.
I can't seem to get an image here on my computer. Are you okay? Can you see me there?
Not live, but yeah.
Yeah, you can see? Okay. I don't know why I don't have an image here. Okay, sorry about that. Yeah. And so what?
They're basically replacing any... So we have these invisible phenomenon, right? We have gravity, for example. We have magnetism, for example. And I'm just going to throw in air into that one because it's also invisible, although it's more visible than the others. But they're essentially taking anything that we can't see empirically. No one can see it. We'll never be able to see it because it's just invisible by all means. But its effects are observable. That's all that we're talking about. We're basically talking about the magic. We're just talking about the effects. So gravity has an effect. Magnetism obviously has an effect. But we're just looking at the effects and not what is causing the effects. That's why they use the word field, because field is basically a catch-all word for the range of effects of a phenomenon.
But they use that also when they use the word energy, when they use the word mass, when they use the word force. They're talking about all these weird, concepts which they introduce in there. And this is where the issue comes in, that these people are just playing around with concepts. They're moving concepts around. I mean, you would think that the word particle needs no sophisticated explanation or definition or any, You don't need to go through all these tangents and clauses and redefinitions and so on. I mean, a particle is a particle is a particle, right? No. Apparently in quantum they had to convert the particle into a field. They had to describe it with a wave function, saying, well, the particle is not always a particle. Sometimes it's a wave, or it forms part of a wave. It's an ingredient of the wave, and what they mean by that is we don't really know where it's at, and so it's got this general wave picture, and it's somewhere in there, and with our equation we can tell you where it's at. So they get into a lot of stuff that has nothing to do with anything. We just want to know what a particle looks like. That's what we want to know.
Could we call a gust of air a field?
That's essentially what it is. A gust of air is a vibration in what we call, if air is a field, and we won't say that it extends all the way to the edge of the universe. We'll just say the air is what covers the earth, right, like a shell, and it gets thinner, less oxygen, I guess, as you go further out until there's none of it, right? Let's call that halo that covers the earth, we'll call it a field of air. So you can take a gust of air or a wind or whatever, just a chunk of it, and say this is a particle. I'm going to call it a particle. You say, what do you mean a particle? Yeah, this little lump of oxygen that is moving, that is vibrating, I'll call that a field. Oh, I'll call that a particle, I'm sorry. And you say, well, yeah, but then what are you really talking about? Are you saying that you're going to collide this against something else? We colliding, bunches of air against another bunch of air? And when you look at the so-called field of, bunch of air, I mean, in the case of air, you can still talk about two lumps of air colliding.
Yeah.
We can all imagine that, but this is not what these people are talking about. These people are not saying those particles that constitute the air, those are just values. So this lump, this quantum ball, this chunk that you took from the field and which you call particle, is not made of like atoms or even particles. I mean, here you have a particle made of particles, essentially, right? But when you look in there, each one is just a value. It's just a value. It's a mathematical value. That's all it is. And so that's why it gets so weird. You have to understand this concept.
But if they're going to use field for all
everything,
invisible objects, basically, or invisible areas of effect, let's call it that, areas of effect, why can't you extrapolate that? Why can't I be a field, for example?
You are a field. According to them, you are a field. You're humans formed a big field, and you're just one lump.
No. I am the whole field. That's what I mean.
Oh, okay. I was looking at it a little different. I was saying all humans, 8 billion form the field, and you're just one little vibrating chunk of the field. But now you're saying you're the field, okay? And what about it?
Isn't field essentially what they're doing is they're basically cookie cutting out. You know how like in Photoshop you copy paste cut paste, you can cut paste.
Yeah.
You basically cut out a shape and say, okay, everything in this shape I'm going to call the X field. And that's kind of what they're doing, and you can do that to anything. You could call this bottle the bottle field, and basically everything that's within that this bottle is I'm going to call a field, but I'm not looking at the bottle. I'm looking at the effect or the room that the bottle takes up. It's like I'm taking out the property of volume out of the bottle, or in these cases of invisible things, we're taking out the property of magnetism, for example.
We're looking at the properties of that region
out of the area without actually looking at what causes the effect. All we care about is the effect, not what caused it.
Right, and that's the
bottom line.
That's the first issue. The other issue, we absolutely have to understand that the field is not comprised of anything solid. It's not comprised of objects. The field that the quantum mathematicians are talking about is comprised of values of mathematical quantities. That's what it is.
But again, because we only care about the
effect.
effects, the numbers, how much it does.
They look at the properties. Yeah. They look at what properties are included in that region. That's all. Something we can measure. You know, what is the size? What is the energy? How fast is it moving? Those kinds of things. Those are the things that the mathematicians are interested in. They call that physics, the study of physics. But what are they studying? They're studying abstract concepts. As Mr. Bourne said, you know, physics has become more and more abstract. He said that in the 1920s. Today it's entirely abstract. There's nothing physical about it. So it's got nothing to do with physics, because physics is physical. Abstract has to do with abstractions. It's the exact opposite of physical. And so, you know, these people are doing abstractions. And what's the abstraction? The main, you can say the bread and butter, the brick that quantum uses today is the field. That's what they deal with from the lowest level upwards. They just talk about fields.
Because field is just shorthand or a synonym for area of effect.
Correct.
And that's all we care about, the effects. So forget anything else. We just care about the area of effect, the field. We have a particle. It has this area of effect. So anything within this area, we're going to call the particle's effect field.
And there's two things you should conclude from that notion. The first one is that mathematics is deemed to be the language of physics. It's deemed to be the language of science.
The language of the universe, I've heard.
On the one hand. And on the other, that experiment is, you know, doing experiments and verifying and corroborating, verifying what the other guy did. Doing experiments is part of not only the scientific method, but an integral part of physics. And the question is whether any of those two belong to physics or to science at all. And I know people are going to roll their eyes and say, hold it, what do you mean experiments are not part of physics? What do you mean that mathematics is not the language of physics? And what you have to keep in mind here is that physics today, what they call physics, actually mathematical physics, has evolved in that direction simply because mathematics is what these people do. So they said, look, very simple, we're going to equate science with math, and we're going to equate physics with math, because that's what we do. Mm-hmm. And what are they doing? They're doing calculations, doing equations. That's on one hand. The other, they're doing experiments. The other branch, you know, the people who go to the lab, the people who go to the accelerator. In fact, the people at NASA who send rockets into the air to do the cosmic stuff versus the other guys who do the atomic stuff, right? And so that's what they do. These guys do experiments, and these guys do equations. And so mathematical physics has evolved as a synonym of science and of physics. And you might say, so what's the problem? Well, the problem is that they ended up with all these irrational explanations, and they dismiss them saying, well, we don't care about the explanations. We don't care about the physical interpretation, because that's not physics. What physics is the equations and the fact that you did an experiment and was able to measure and bring me a measurement that I can use in the equation. So that's what the whole thing has evolved to. And I'm saying that we have to stop this. We have to rethink what is the purpose not only of science but of physics. And when you look at that and you say, look, if physics is about rational explanations, these guys are completely off the mark. These guys are not doing physics or science. And, you know, again, the language of physics, as far as I'm concerned, is not math, and we don't have to do experiments. Experiments we have to explain, not do them. You can do all the experiments you want. I can drop the pen 1,000,000 times. That doesn't mean I'm going to understand why that pen falls to the floor. I got to come with an explanation for that phenomenon, or for two magnets that attract each other. That's one part. The other part is we do them with objects. The language of physics is not mathematics. The language of physics is illustration. I should be able to show you a movie of my mechanism, and you should watch the movie and pretty much understand what I'm talking about.
Blind guys can't do physics, you racist.
I can explain it to him, in his ear. Well, a blind man probably wouldn't be able to do equations either, for that matter, or do experiments at the lab. He probably wouldn't be able to find the lab without his dog, But my point here is that the language of physics, I won't say science because I divide also science into philosophy and physics, but the language of physics is illustration. You should be able to do physics. I mean, you can't do physics without an object. What is an object? That which has shape. Very simple. And so if you're going to do physics, you better have an object. That means you should be able to put a shape, some kind of shape on each one of the frames of your film and show me the movie of what your mechanism, your proposed mechanism is. That's the theory. And to say, well, no, what we do is describe, and here's the equation. Well, what did you do? Let's replace the variables in the equation with a number. Bum, 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 bum. I replace the 10 variables and the constant, if necessary, in your equation with some numbers. Fine. I get one result, 1 point. That's all I get. So I plot that point. I'll plot it on a chart. Now I replace all the variables with another number, and then with another number, and with another number, and I keep plotting all these points, and I get a trend. Well, that's what math does. What have I done? All I did was characterize motion. What I've done is just watch how something is behaving or moving or whatever. That's all I've done, and it's a description. That's all an equation can do. And the question is whether physics, is just describing. You go to the show. You watch the magician, and he cuts the lady in half. So what did he do? Are you just going to say, well, he cut her in 2 pieces, had 20 strokes of the saw, he did it in 15 seconds? That's all description. You haven't explained any. What I want to know is how he did the trick. That's what I want to know. That's where you have to burn, some gray matter. But to say that, the guy cut her in 15 seconds with 20 strokes of the saw, that's a description. Is that science? And that's where we have a difference.
I would say they're only doing half science.
Oh, half.
I would put what they're doing as the necessary part, but not the integral part. The whole point of science is to explain things, but you kind of need a starting point. You kind of need to know what it is you're going to explain, and it's nice to have the guy drop the pen. It's nice to have them, exactly, describe every single inch of what you are to explain. So you kind of need, the paleontologist needs to find a bone before he can explain where it came from, that kind of thing. Okay. So I would still put that in science and physics, but it's kind of like the grunt work part. It's kind of like we have to do that obviously at some point. It's like someone has to put the tools up for the magician. The magician can't do the trick without any of his.
Well, yeah, you can't explain boxes, if you haven't seen what he's going to do or what he did.
Something to work with, but that's not the. That's kind of like the first half. Like, okay, that's great. That we're doing a lot of prep work for the science, but we're not doing the actual science part. The juice of the right. Lemon. We just have a whole bunch of lemon rinds, and we don't have the juice of the lemon.
And that's why I separate that. I'm saying, what he just referred to is the description part, and we include that, if you want to call it a description, we include that under what we call the assumptions or hypothesis. What is the hypothesis? The hypothesis includes, first, the objects that you're going to use. Second, the definition. You got to have those straight, the key definitions. And then the what he was referring to is, the initial scene, or what you're going to be explaining. So you have to have some event. You describe the event. You say, look, the magician cut the lady in half. Okay, and that's just a very quick summary, right? And that's part of the hypothesis. That's part of the assumption, because you're explaining to someone who didn't see the magician cut the lady in half. So you say, look, let me tell you what I'm going to explain. I'm going to explain that there was this man on the stage and he cut the lady in half. So many strokes, so many seconds. He cut her in 2 pieces. She came back in 1. Great. That's what happened. So that's what you're going to explain. And now the guy says, okay, explain it. How did it happen? What was the mechanism? And that's where science vibrates, because now you got to burn some gray matter. You got to burn some neurons in there to try to figure out how did he do that? How did he do that trick? That's where science vibrates. To say that he cut her in half, well, that doesn't take any. I measured. There were 2 pieces. Now there's only 1. I mean, what is that science? That's the question.
I equate it more to the detective analogy, because when a detective gets to a crime scene, he still has to pick up the clues and look around and kind of gather information. Describe it, the scene perfectly, or is it at least the crucial parts, or what he deems crucial. Let's put it that way.
Okay.
But physicists nowadays are stuck on that part. They're stuck on the gathering information part, describing. Okay, can we get
collect information, please, lab
sir,
boy, go collect the data.
We have the detective. There are 2 years at the crime scene, still picking up clues.
They don't have an explanation for how the murder happened.
Can we explain the murder? The murder has already got away. Let's get to it, buddy.
That's a good analogy. Very good analogy. I love my son because of that. He comes up with all these analogies, and that's a good analogy. Imagine a detective. Here we have Sherlock Holmes and his buddy, and they go to the crime scene, and they spend the rest of their lives just describing there was blood here, and the victim fell from the stairs, and she had a knife stuck to her back. Fine.
The victim fell from the stairs. No, there's a corpse on the floor.
There's a corpse on the floor with a knife stuck to her back.
At the bottom of the stairs.
Yeah, and the question is,
and hold on, and we're not done, because we have to measure their thigh, we have to measure their toe. We have to measure everything. We have to
the length of the knife,
and they're also doing tests. They're dropping people from the stairs to see if they fall if they make the same shape when they land on the floor. Didn't that time? Let's do it again. Oh, we notice when people.
Let's see if it's repeatable. So you do it too. You go to another in Australia. You do that too. See if you drop from the stairs, you end up in the same way. So they do all this stuff. Right, that's true, and they do a lot of measurements, a lot of numbers, a lot of equations. And they can never tell the judge or the jury, look, this is what we think happened. They can't tell you, or they'll say...
They try, but they come up with these patchwork, who cares
irrational.
About the real explanation?
Yeah,
Let's just give them something.
But that's a good analogy.
It's
they
don't really care about the explanation part. They kind of do, they care, but again, they confuse explanations.
No, I'll tell you how they explain...
It's like you said, they confuse explanations with descriptions.
But you know how they explained it to the jury? Let me tell you how they explained it to the jury. Says, well, the victim died in this universe. In a parallel universe, she continued to live, and in another one, she won the lottery, and so on. So they have all they have the multi-universe theory, where every event breaks up into all these gazillions of universes, and in this universe, she died, and she was killed. So they don't have to explain it because. It's just that's how the wave function collapsed here. In another universe, the wave function maybe doesn't collapse, or who knows, or collapses into something else, into a eunuch or a leprechaun, for all we know. This is the issue. The issue that these people never explain to the jury what they think happened, how they think it happened. They just do measurements and equations and spit out facts. And they say, oh, we've proven it. Yeah, what did you prove? I proved the fact. I proved what happened, not how it happened. That's the issue.
I like the pen dropping experiment. That's how we discovered
you
gravity.
do it many times.
You just have to do it once, and it's amazing when you do that experiment, because the pen goes it moves on its own. When you let go of it, it goes straight down.
It doesn't stay there. You would think it should stay there, and it doesn't. For some reason, magically, it always goes down. It never even goes up.
But that's not my point. My point is, everyone always says, well, you have to do experiments to find out, out empirically. Everyone's always harping on experiments and proof.
Right.
But the pen dropping one cuts through all of that. Look, anyone can do that experiment. I mean, you could call it a straw man argument because it's not a real experiment or whatever, but
it's good. It is a good experiment.
Either way, you have to explain how that happens.
Right.
Not describe how fast the pen's falling.
Right.
Not describe the shape of the planet. Not describe angels. Unless that maybe.
Well, maybe that's my theory. Angels
describe
took
everything
it down.
that you're gonna use to explain, but explain. Get to the point already.
Yeah.
It's no matter who does that, they have
true.
to explain that phenomenon.
And that's totally true. You got to get, at some point, you got to have an explanation for that. I mean, if I just keep dropping pens and say, I repeated the experiment, I verified his prediction, it does fall at 9.8 meters per second square acceleration, et cetera, et cetera, et cetera. What have you done? And here's the equation, Newton's equation, mass times mass divided by distance squared. All that is just a description. You have not explained the phenomena. And okay, so that's regarding quantum, okay? But it doesn't stop there. We also have the problem where, we have it also in general relativity, which deals with something else, which deals with our cosmic world. And specifically, it deals with space-time. And here you have, the question is whether you can, and again, they're dealing with concepts here. You add space with time and you end up with some kind of four-dimensional object. Unimaginable, as they tell you, because they'll concede that it's unimaginable. And I'm saying, can you add a 3D rock, right? Here's the rock. It's three-dimensional, hopefully, right? I hope you can see that it's a three-dimensional rock. And add time any way you want. You can argue that it happened at 2 o'clock in the afternoon. That's an event. That's when you saw the rock or when you picked up the rock or whatever. Or you can say the rock flew for 3 seconds. Just take it any way you want. Do you end up with a four-dimensional object because you unite a 3D rock with time? And what they do is they end up in mathematical physics. They end up with this object. They say if you add space, 3D space, by which they mean a volume, some kind of object, right? And you add it to time, whether it's at 2 o'clock in the afternoon or just the 3 seconds that went by, you end up with this, with some kind of four-dimensional object, which in this case, as you can see, it's a two-dimensional object that shows that apparently depicts a three-dimensional object. So it's a projection of a three-dimensional object in 2 dimensions, but as you can see, it's moving. Okay, that's, I guess, the motion part is the 4th dimension. Is this a four-dimensional object? I mean, I can imagine this one, so why do you say that's unimaginable? If it's unimaginable, it's because what you are staring at is not what they're describing mathematically.
That's a trippy GIF.
I know.
The GIF is really trippy.
Yeah, but see, the issue
what
here...
you're saying is basically there's no such thing as a four-dimensional picture. There's four-dimensional GIFs and four-dimensional videos because it always has to have time involved.
Right, and the question is whether, and again, if I take a rock and I add time to it in any way you want, 2 o'clock the event happened, 3 seconds is what happened, I don't care. Just add time any way you want. Does that convert the rock into a unimaginable four-dimensional object? And obviously that's nonsense, especially when they follow that up and say, oh, by the way, we warped the rock. We warped rock time. So not only do we have an unimaginable object, but we warped it. We warped the rock and time. We did it with gravity. Now, does that make sense?
It sounds cool. I don't know if it makes sense, but it sounds cool. When you got a gravity sucking up your 4th dimension, and a black hole comes in and sucks you to another dimension, we got some magic on our hands. We got a good movie there.
Yeah, and so this is
you
the
want
issue.
A movie, I can make you a real good movie. It doesn't explain anything, but it'll amaze you.
Yeah, and so this is the issue. The issue is not only quantum, because some people say, well, quantum we don't understand, but everybody understands general relativity. No, that's nonsense as well. If we go by the rules that I establish here for what is rationality.
That sounds douchey, but go on.
Yeah, okay.
If we go by my rules.
By my rules, okay. If we go by the definition, the criteria that we have for rationality, and the first item on the list is concepts turned into objects. Space-time is a concept. You can't say space-time is a physical object. And that's what they say. They say that space-time is an unimaginable object. And you say, what kind of object is it? What's a mathematical object? What do you mean a mathematical object? Is it an object or not? What do you mean mathematical? Mathematical means we can describe it mathematically with an equation. but we can't show it to you because it's unimaginable. Well, then are we describing or explaining or whatever the real world? I mean, are we referring to the real world? If it's something that's unimaginable, and that's when they add and they say, well, our minds are so puny, we're just mere humans, we're not gods, so this is beyond our comprehension. No kidding. And this is the problem. The problem is that they never get to explain anything, like Mary Poppins, because what happens?
What, Mary Poppins?
Yeah, Mary Poppins.
Explains things or doesn't explain things?
No, it's the banker asks her, Mary Poppins, will you please explain this? Like, what happened here?
Explain yourself.
And she looks at him and says, I want to make one thing absolutely clear. Yes? I never explain anything. And that's essentially what the mathematicians do. They never explain anything. Yeah, you can get to the end of the onion, the center of the apple, and you won't find any seeds. There's nothing there. You never get an explanation. And of course they dismiss that, saying, well, we don't do explanations because the human mind cannot comprehend all this stuff, because the common sense of the universe is not the same as the common sense of us petty human ants. That's their answer. And that's where it ends. The question ends. We have Martin Arhul here.
Question. Do they, quantum and general relativity, claim to explain the nature, or are they claiming they illustrate math? I mean, do they acknowledge the difference between explanations and descriptions? Probably not.
No. Well, hold it. No, let me clarify that. That is an important question, because it goes like this. Some mathematicians, like you'll get this guy, Donald Simonek, which I always quote because that's one of the quotes I found there. He's from the University in Pennsylvania, and he's an emeritus professor. And he says, science doesn't explain, science describes. It seems like he establishes a difference between a description and an explanation. And I know there's other people out there. The other one I found out there, and I'm trying to get more of these evidences out there, so I hear it, so that we can produce it from the horse's mouth. The other one is Steven Weinberg. He's a Nobel Prize, famous Nobel Prize winner, University in Houston in Texas. And I think it was maybe Austin, Texas. But the point is that Steven Weinberg, I've got him here on YouTube, and he says, mathematics doesn't explain. Mathematics only describes. So at least I've got two sources. Hopefully there's some more out there. But the point is, these people apparently seem to understand the difference that, an explanation is not a description. But see, if you read the article I wrote today, you get people like this other fellow from UCLA. His name is Lincoln. I can't remember his first name, but whatever it is, Lincoln. And he explains, so he begins his video that way, saying he's going to explain how magnets work, and you're going to understand today how magnets work. And he goes through all this 7 or 8 minutes of video, and then he finally says, this is the bottom line. He says, well, the electrons spin in the same direction. Like both of them spin clockwise. Great. So what have you explained? All you did was describe. You described that every time a magnet attracts another, you find that the electrons spin in the same direction. That's a description. You haven't explained how the fact that, like I say, 2 basketballs turn into... You come into a room, you find 2 basketballs that are turning in the same direction. They're approaching each other. Why are they approaching each other? Is there a wire wound around their equators? Is there air pushing them together? What's the cause? What's the mechanism? By saying that they spin clockwise, both of them, you're not explaining it. You're just describing. And so the question is, do all these mathematicians understand what a description is and separate it from what an explanation is? And you got the other case of another Nobel Prize winner, Richard Feynman. He claims to explain how magnets attract each other also. And he does a big mess of it. He takes 8 minutes to say he doesn't know. And again, he goes into the same rigmarole. He says, it depends on the level you want to understand it at. Well, I want to understand it at the baby level, at the kindergarten level. Please make it as simple as possible. Well, he says he can't do that. That you got to go to the university to understand how a magnet attracts another.
You're
Why?
Too stupid,
Because
you're too stupid.
Huh?
You're too stupid.
Yeah.
Sorry.
No, because they want to introduce math. And I don't want math because math can only describe according to Weinberg and according to Donald Simonet. So please don't bring your math. Just tell me what the trick is. Tell me how the magician did the trick. That's all I want to know. And they can't do that. They can't do that because in order to do that, you have to make an assumption about the invisible entities that mediate. And that's where the problem is. These people, and some of those people, and I think even many of the Nobel Prizes out there, they don't understand the difference between a description and an explanation. And so whether they do or not is still up in the air. I'm not sure they do understand. They probably, if you push them against the ropes, they'll say, well, a description is an explanation. Well, I thought you said that science doesn't explain, that science describes. What did you mean? So it's up to them to tell us to define the terms description and explanation so that we can understand whether they understood. And I don't think they really got that yet. They don't have a definition for these key words. They just use them, and they probably just refer to whatever's in the ordinary dictionary. I don't think they understand. So that's my answer to you, Martin.
I got a big Nobel Prize question right now.
Whoa! We got a Nobel Prize question, please.
You ready for this?
Hold it. We got drumbeat here.
This one's going to be, I think, more of a philosophical or religious question, but it might be science.
We're going into religion, philosophy here.
Let's assume, and it's not a far-fetched assumption, let's assume we have a mathematician, right? Mathematical physicist.
So we visit the asylum.
Yeah,
Okay.
we go to the asylum.
Okay.
And this guy, just for the sake of it, I mean, this is for all you mathematical physicists out there. You could probably answer this one, not my dad, but I guess the question is, could there be a more precise mathematical equation that mathematicians aren't using since they're looking in the wrong place, since they're always looking in the same place, that could describe the rope model and thereby all the phenomenon in the universe? Or, I guess better phrase, is the equation for the grand unified theory and all the equations that everyone's looking for hidden in the equations used to describe a twined rope?
And I can answer that question. Fortunately, I can. And there's a couple answers to that question. The first one is we do have an equation, and it's C equals wavelength times frequency. It's been settled. We don't need to look for something because this equation has been around. It's a derivation from Maxwell's 4 primary equations, okay? C is a constant. C is the velocity of light, the velocity of light. It's equal to frequency times wavelength. If you reduce the frequency, because they're inversely proportional, when you reduce the frequency, you have to increase the wavelength and vice versa. Okay, so they're inversely proportional because the speed of light has to remain constant for whatever reason. Let's not worry about right now the physical reason it remains constant. Let's just say one goes up, the other one goes down. So we do have an equation for the rope. That's the first issue. What's the second issue? The second issue is that, as far as I've been looking at, if you go through the internet, you won't find an analysis of torsion waves. What you will find lots and lots and lots is...
What's a torsion wave?
Okay, so let's go through that.
What's a torsion wave?
Okay, let's go through that. When Huygens, really even before that, Robert Hooke was the guy, as far as I know, Robert Hooke's the guy who introduced waves. He did that in the 1650s, okay? He did that quite early. A few years later, we have Huygens who picks up on this and he writes his wave book,
Real quick, but we're not talking about torsion waves, we're talking about waves, right?
We're talking about waves in general, so let's start there.
Okay.
We have, because we'll see how this progresses, okay? And Huygens goes in there and analyzes waves, but what does he analyze? He analyzes longitudinal waves. That's what he thought, light was, and that's how he analyzed it in his book, seminal book known as The Treatise on Light. That's what his book was called, okay? And Newton opposed that. He says, no, I don't agree that light is comprised of waves. I think it's particles, and so they came with this particle and wave fight.
Do we need to know what a longitudinal wave is?
Yeah, it's like, when you see sound waves.
Oh, the one going at
Yeah, it moves in the direction, in other words, back and forth, right, in the direction of motion.
Mm-hmm.
Okay, of travel. And that's more or less what you have also for, to some degree, for water waves. And that's what he was visualizing. He was kind of explaining it in those terms. Then it wasn't until, the 19th century, early 19th century, you have Augustin Fresnel. And what he does is he says, no, look, we've been mistaken all these years. Really, it's a transverse wave. And
let me stop you there. So right now we have
longitudinal.
We have air waves, sound, water waves, which are like going over.
They're kind of intermediate. Yeah.
And now we have
transverse waves
and torsion waves.
Hold it. But transverse waves means that
a lot of waves.
And it's a two-dimensional. See, the longitudinal wave is considered a one-dimensional wave because it just moves in a straight line, just back and forth along the same axis. Whereas now you have the transverse wave, which is introduced by Augustin Fresnel in France, and he says, look, this thing is an oscillation that goes up and down perpendicular to the motion of the wave. That's why it's called transverse wave, because it's moving up and down. Like if you take a rope and you shake it up and down, you'll see the goosebumps, right?
We're back to the rope, right? I see what you did there.
Okay, so we have the goosebumps. And so those two waves, the longitudinal wave and the transverse wave, have been analyzed to exhaustion. And one of the guys who did the transverse wave to exhaustion is Mr. Maxwell. James Maxwell worked on transverse wave. He was convinced light was a couple of transverse waves, electric and magnetic, that ran perpendicular to each other. So he did a full analysis of that. You don't need to do any more, because all you got to do is read Maxwell and you're done. Everything you wanted to know about transverse wave pretty much came out of him. And that's why he's a hero in the mathematical world. What no one has done, Maxwell, Huygens, any of those, is look at torsion waves. And what is a torsion wave? Torsion wave is you take a rope, you take it straight. It's already straight. So you don't have to wave it up and down, you don't have to move it back and forth, none of that. All you do is torque it. It's a torsion that moves along the wave, along the rope. So you take your grandmother's rope and you put two clothespins. You touch one, and if you try to film it, like I've tried to do that, I've really done this, you can't see how fast the other guy moves. It moves instantaneously.
There's a YouTube channel called Slow-Mo Guys who do a lot of things. They just keep doing things and they put it in real slow-mo. Like they'll throw a water balloon against a wall and film it with a really slow camera.
Right.
And I guess that would be one for them, where they take a clothespin and go like,
say if you can film it,
trillion frames per second. You turn one clothespin, see how long it takes until the other one moves.
And nothing beats a torsion wave. Nothing. No car, no airplane, no rocket. Nothing in this planet that you can imagine beats a torsion wave. And that pretty much tells you something about the nature of light, because light is kind of fast. It's swift. It's 300,000 kilometers per second.
That sounds fast.
And yeah, it is. And so the question is, here you have a model for the swiftness of light first. Second, you have the links that verify Maxwell's equation. C equals frequency times wavelength. Wavelength becomes shorter. You have more links, more frequency. Frequency becomes lower, you have lower frequency, you have longer wavelengths.
per same distance.
There you have it. This is what they're describing. They've been describing. You torque this, the more you torque it, the more links you have, and the shorter the link, and vice versa. When you untorque it, what you have is fewer links and longer links. So C equals F, frequency times wavelength, is the equation of a rope. There's no other entity that you can imagine that can simulate, that you can use to simulate that equation. That should give you got the speed, you got the inverse relation between frequency and wavelength. It's just like, this is it. And these guys are still dealing with transverse waves and saying, well, we left the longitudinal wave in the past. But there's one more thing we should understand about this, and that's that during earthquakes, right? This has been measured. This has been already verified by the mathematician. Proven. We have proof. During earthquakes, longitudinal waves, like air that move back and forth, move 1.7 times faster than transverse waves up and down. So they measure these things. The geologists that analyze these things, they say, look, we looked at they have a way of measuring these things, and they say, look, the longitudinal wave moved faster than the transverse wave. So we get it. The world in expect. Yeah, but my point is, we have the world in reverse. Here you have the torsion wave, which is swift as like now, instant. And that leaves the poor longitudinal wave in the dust. And the longitudinal wave leaves the transverse wave in the dust, and they're saying light is the transverse wave.
The slow one.
The slow one. That's the world we have today. Thanks to the mathematicians. They have it completely in reverse.
Back to that question.
Yeah, and they don't have any analysis of torsion. If you look up there, you won't find too much information on the torsion waves.
That's my point. That's where the next noble is hidden in torsion waves. Because if you get, because I'm sure there's more ways to describe a torsion wave than the one you proposed, the one that with the inverse. Oh, we have a question from Thomas.
Yeah.
Is torsion on a normal rope speed of sound? Speed of light. Maybe.
Yeah, no, it's the speed
of
light. Not speed of sound. No, remember the speed of the sound is measured in 400 meters.
Meters.
Meters, not kilometers. Meters per second. It's like between 400 and 600. I can't remember.
We've gone faster than the speed of sound.
Yeah. Jets go faster than the speed of sound. So no, hopefully not. Be the cause of it.
Perhaps late, but could superimposed ropes be the cause of redshift to galaxies? Oh shit!
Well, let me tell you, if you look at why God doesn't exist, it'll tell you what the redshift is due to. Okay, and I don't know if you've heard of this fellow who was kicked out of the United States. What was his name? Died recently, like 1 or 2 years ago. Anyways, he fought that. He said the redshift has nothing to do with the receding galaxies. And to some degree, I think he's right. He was saying the CFeed stars out there, he's saying we're confusing distance with shininess, okay? But that's one argument. The other argument is the one I have, and that's that, as a rope comes out of an atom, distant atom, and as it approaches us, it does slowly... the links become longer and longer, and that's your redshift right there.
I think that's what you'd expect.
Right, and that's the redshift. That's the cause of the redshift.
In fact, if you take the clothesline experiment,
here we have it,
and you just turn one end of it,
right,
until the tightness of that goes along, it starts widening out.
And that's the point. That's where the redshift comes in. Yeah, right. So when a galaxy approaches you, it pushes all the links, tends to push the links together, and that's a blue shifted. That's why when it approaches you, it's a blue shifted galaxy. For example, Andromeda is approaching the solar system, and because Andromeda is approaching us, Andromeda is blue shifted, and that violates the the Big Bang theory, because Big Bang supposedly everything's going outwards. Okay, and conversely, anything that is receding from us would tend to, make the links longer, and that's why it's redshifted. So it doesn't have to do with, in other words, it does have to do with whether a galaxy is approaching or not. Where general relativity fails is in explaining why Andromeda Galaxy is, and all the ones in the in our what is called the local group, which is about 20 galaxies, why they're blue shifted. And so they had to put a little fix in there, and they said, well, the reason they're blue shifted is that electromagnetism is overcoming gravity. That's the solution they have today. They say, look, the electromagnetic forces, magnetism specifically, magnetic fields, they're overcoming gravity. But it turns out, this galaxy is in the middle of nowhere. It's millions of kilometers away, millions of light years away. And you're saying, what, the magnetic field of our galaxy is reaching all the way up there and overcoming the gravitational attraction, or in this case, the opposite, because, you can't explain it, because what they're saying is the Big Bang is pushing the galaxy outwards because everything's exploding, right? The hand grenade.
We're pulling
but it turns out that the electromagnetic field of our galaxy is overcoming that expansion and pulling Andromeda inwards. Well, if you want to believe that, you might as well believe in witches.
This question, I really like this question of redshifted galaxies with the rope model, because there's a thing that we haven't talked about there, and I don't want you to explain it now because we're out of time.
The Doppler shift.
No, but there's friction in the rope, because if that signal, essentially what we're saying is the longer a signal travels, the more torsionness it leaves behind. It leaves its energy behind, so to speak. The longer it travels, it's kind of leaving more and more motion behind until at some point it's barely any motion going out. So there's this weird hint or clue of how the ropes behave in the redshifted nature of the length of signal.
Yeah, but keep in mind that we have to explain why we can see the Andromeda galaxy. And we do see it, but we see it blue shifted. So we have to explain those both phenomena. Why it's blue shifted and why we can see it. And, what are we going to say? We have to explain it under the rope model. I think there's no problem. With particles, I don't know. You tell me how we're going to explain it with particles. And that's homework for Sunday. So we'll see you then, same time, same station. We'll see you then. Bye-bye.